Let's practice evaluating projectile motion in 1D by considering a ball thrown up in the air. This is Ted. He'll be throwing the ball up in the Z direction, and the initial position of the ball is 1.5 meters above the ground. The initial velocity with which Ted can throw the ball, let's say, is 11.2 meters per second in the upward direction. It's a pretty fast throw, but that's okay, and we'll define the initial time to be 0. Now, the ball goes up in the air. And at the maximum height, well, we don't actually know the value of the maximum height. That's one thing we'll have to solve for. But we do know the velocity when the ball reaches its maximum height. In one spatial dimension, if the ball goes up and comes back down, it has to be moving with a velocity of 0 at its maximum height. If it isn't, it must not be at its maximum height. We don't know the time at which this happens. That's another thing that we'll solve for. Now let's get Ted out of the way. Thank you, Ted. And now the ball will fall back down to the ground. And of course, we know the height of the ground. We defined it to be 0. And we don't know the velocity with which the ball hits the ground. And let's imagine that we also don't know the time at which the ball hits the ground. You can see that we've listed 9 variables. The 5 in black for which we have numerical values we know. The 4 with question marks in red we don't know. And we're going to solve for those in this problem. Let's organize things by arranging them in order and putting everything in a table so that we have all the positions, velocities, and times in one place. Get rid of those lines. Now, of course, we also know the value of the acceleration near the surface of Earth for an object in free fall, which is negative 9.8 meters per second squared. Once the ball is in the air out of Ted's hand, before it hits the ground, we consider the ball to be in free fall, meaning that it experiences this acceleration. We also know the 3 equations for 1D motion with constant acceleration, certainly fulfilled by this problem. Now, those are written in terms of an x variable, but you can always wave a magic wand and write them in terms of z, right? Physics doesn't care whether you label it with an x or a z. So now we're going to go through and solve for the unknown variables in order using the equations of motion and the givens of the problem. So let's start with z1. Remember, that's the maximum height that the ball will reach. Which of the 3 equations of motion should we use? Certainly you don't want to try using all 3 at once. Looking at this problem, we don't know t1 yet. So I would avoid any equations that involve time. Well, that eliminates the top 2, right? First one involves time, let's get rid of that. Second one involves time, let's get rid of that. Those equations are subject to recall later, but for now, for this part of the problem, we won't use them. We'll use the one involving velocities, accelerations, and displacement. So our goal is to solve for z1. Let's write that equation in terms of the variables that we do know. So that becomes v1 squared equals v0 squared plus 2a delta z. And I've subscripted delta z so that it's clear we're talking about the displacement and going from position 0 to position 1. I can expand that to make it even more clear. That just becomes z1 minus z0. That's that displacement. So now our goal is just to solve for z1. Well, we can subtract off v0 squared from both sides, divide both sides by 2a, and now just add on z0 to both sides, and we get an expression for z1 in terms of the other variables that we do know. We have all the variables in the table, so let's plug in their values. The only challenge here is to make sure that you retain the correct sign on the acceleration. If you didn't do that, you might accidentally subtract something off from 1.5 meters instead of adding something on, and of course it makes sense. The maximum height should be bigger than 1.5 meters. Okay, we'll go through and simplify a little bit, canceling out those minus signs. That second term becomes 6.4 meters. We add those two together. You can do this in your head. z1 equals 7.90 meters. So that's the maximum height that the ball reaches as measured from the ground. Remember, Ted was throwing from 1.5 meters up. Now that we found that variable's value, let's put it into the table. And we'll move on to solving for t1, the time at which the ball reaches its maximum height. So if we want to solve for t1, which equation of motion should we use? Well, we can definitely eliminate the one that doesn't involve time now, the one we just used. We need to solve for time. That would be a bad choice. The other two, actually, in this case, they work equally well in the sense that we know all of the other relevant variables. Of the two, I would pick the first one just because it looks simpler. We know the initial and final velocity, we know the acceleration, let's just use that to solve for the time. So for a ball going from position 0 to position 1, that equation becomes v1 equals v0 plus a times t1. Technically it should be t1 minus t0, but t0 is 0, so I just left it out as your book often does. Let's rearrange this to solve for t1, so we subtract v0 from both sides. Now we'll divide both sides by a, and we have an expression for t1. We can plug in the variables, and we're sure to watch our minus signs carefully to get that t1 is 1.1429 seconds. Let's round off to 3 significant digits to find that it's 1.14 seconds. So that's how long it takes the ball from the time it leaves Ted's hand to reaching its maximum height. Okay, we'll put that in the table. Next variable to tackle is v2. Remember, that's the final velocity right before the ball hits the ground. Okay, we'll erase all of our work. We want to solve for that. Which equation should we use? Well, we want one that involves velocity, but not time. Remember, we don't know t2. It's very similar to the first variable we solved for. If we don't know t2, I would cross off the first two equations of motion and go with that last one again. Now we're going to rearrange it to solve for v2. So to start, it's v2 squared equals v1 squared plus 2 times a times delta z, now going from 1 to 2. So remember that displacement is z2 minus z1. Now we just need to solve for v2, which we can do by taking the square root of both sides. But remember, v2 technically is equal to plus or minus the square root of the right-hand side, and in this case that's important. Think about it. v2 is the velocity of the ball right before it hits the ground. It is definitely moving in the negative direction at that point using our convention of positive z pointing up, so we have to choose the negative sign out in front of the square root. We plug in all the values of the other variables from the table, making sure to track our negative signs carefully inside the square root. If you get the square root of a negative number for a problem like this, you definitely mess something up. You should go back and figure out what it was. But in this case, we have a positive value under the square root. We'll take that square root and find that v2 is minus 12.4 meters per second. So that's our answer. We'll plug that into the table. And now the only remaining task is to solve for t2, the time at which the ball hits the ground. Okay, which equation should we use in this case? Well, we need one that involves time, so you definitely want to eliminate that bottom one. Just so that it doesn't feel left out, I'll use that longer middle equation this time. Okay, so let's write that equation out in terms of going from position 1 to position 2. We do that. And this simplifies considerably because you'll notice that this term contains a v1. Well, in our problem, v1 was 0, right? It had 0 velocity at its maximum height, so we can just get rid of that middle term. Things simplify considerably. And I'll write out explicitly that the time interval in going from position 1 to position 2 is t2 minus t1. All of that has to be under the square, remember? Now all we need to do is solve for t2. So let's subtract z1 from both sides. We'll multiply both sides by 2 and divide both sides by a. Now we'll take the square root of both sides. Now again, it's technically the plus or minus square root. Thankfully this is a time interval, so we should choose the positive value. And now we just add t1 to both sides to have an expression for t2. All we need to do now is plug in the variable values to get our answer for t2. So we plug in the values. As always, we're sure to track negative signs carefully. And we get out that t2 is the sum of those two numbers, which is 2.41 seconds. We'll write that value in the table, and now I'll summarize briefly. Ted started with the ball at a height of 1.5 meters and threw it up in the air with a velocity of 11.2 meters per second. That was at time equals 0. It reached a maximum height of 7.9 meters, of course had a speed of 0 when it reached the maximum height, and it took 1.14 seconds after Ted threw it to reach that maximum height. 2.41 seconds after Ted threw the ball, it hit the ground, and it had a velocity of minus 12.4 meters per second right before it hit the ground. The good news? If you can correctly set up and solve a problem like this, you should be in good shape when encountering any 1D motion problems with constant acceleration and those three equations of motion.